Ferrous metallurgy involves processes and alloys based on iron. It began far back in prehistory. The earliest surviving iron artifacts, from the 4th millennium BC in Egypt, were made from meteoritic iron-nickel. It is not known when or where the smelting of iron from ores began, but by the end of the 2nd millennium BC iron was being produced from iron ores from China to Africa south of the Sahara. The use of wrought iron was known by the 1st millennium BC. During the medieval period, means were found in Europe of producing wrought iron from cast iron using finery forges. For all these processes, charcoal was required as fuel. Steel was first produced in antiquity as an alloy. Its process of production, wood, was exported before the 4th century BC to ancient China, Africa, the Middle East and Europe. Archaeological evidence of cast iron appears in 5th century BC China. New methods of producing it by carburizing bars of iron in the cementation process were devised in the 17th century. During the Industrial Revolution, new methods of producing bar iron without charcoal were devised, and these were later applied to produce steel. In the late 1850s, Henry Bessemer invented a new steel-making process that involved blowing air through molten pig iron to burn off carbon, and so to produce mild steel. This and other 19th century and later processes have displaced the use of wrought iron. Today, wrought iron is no longer produced on a commercial scale. Meteoric iron. Iron was extracted from iron-nickel meteorites, which comprise about 6% of all meteorites that fall on the Earth. The source can often be identified with certainty because of the unique crystalline features of that material, which are preserved when the metal is worked cold or at low temperature. Those artifacts include, for example, a bead from the 5th millennium BC found in Iran, and spear tips and ornaments from ancient Egypt and Sumer around 4000 BC. Meteoric iron has been identified also in a Chinese axe head from the middle of the 2nd millennium BC. These early uses appear to have been largely ceremonial or ornamental. Meteoritic iron is very rare, and the metal was probably very expensive, perhaps more expensive than gold. The early Hittites are known to have bartered iron for silver, at a rate of 40 times the iron's weight, with Assyria. Meteoric iron was also fashioned into tools in the Arctic, about the year 1000, when the Thule people of Greenland began making harpoons, knives, ULOS and other edge tools from pieces of the Cape York meteorite. Typically pea-sized bits of metal were cold hammered into discs and fitted to a bone handle. These artifacts were also used as trade goods with other Arctic peoples. Tools made from the Cape York meteorite have been found in archaeological sites more than 1,000 miles distant. When the American polar explorer Robert Peary shipped the largest piece of the meteorite to the American Museum of Natural History in New York City, in 1897, it still weighed over 33 tons. Another example of a late use of meteoritic iron is an adze from around 1000 AD found in Sweden. Media related to objects made from meteoritic iron at Wikimedia Commons. Native iron. Native iron in the metallic state occurs rarely as small inclusions in certain basalt rocks. Besides meteoritic iron, Thule people of Greenland have used native iron from the Disco region. Iron smelting and the iron-age. Iron smelting, the extraction of usable metal from oxidized iron ores, is more difficult than tin and copper smelting. While these metals and their alloys can be cold-worked or melted in relatively simple furnaces and cast into molds, smelted iron requires hot working and can be melted only in specially designed furnaces. Thus it is not surprising that humans mastered the technology of smelted iron only after several millennia of bronze metallurgy. The place and time for the discovery of iron smelting is not known. partly because of the difficulty of distinguishing metal extracted from nickel-containing ores from hot-worked meteoritic iron. The archaeological evidence seems to point to the Middle East area during the Bronze Age in the 3rd millennium BC. However, iron artifacts remained a rarity until the 12th century BC. The Iron Age is conventionally defined by the widespread replacement of bronze weapons and tools with those of steel. The transition happened at different times in different places. As the technology spread, Mesopotamia was fully into the Iron Age by 900 BC. Although Egypt produced iron artifacts, bronze remained dominant until its conquest by Assyria in 663 BC. The Iron Age began in Central Europe about 500 BC and in India and China between 1200 and 500 BC. Around 500 BC, the Nubians, who had learned from the Assyrians the use of iron and were expelled from Egypt, became major manufacturers and exporters of iron. Ancient Near East. One of the earliest smelted iron artifacts, a dagger with an iron blade found in a Hattic tomb in Anatolia, dated from 2500 BC. About 1500 BC, increasing numbers of non-meteoritic smelted iron objects appeared in Mesopotamia, Anatolia, and Egypt. 19 iron objects were found in the tomb of Egyptian ruler Tutankhamun, died in 1323 BC, including an iron dagger with a golden hilt, an eye of Horus, the mummy's head stand, and 16 models of an artisan's tools. An ancient Egyptian sword bearing the name of Pharaoh Meneptah, as well as a battle axe with an iron blade and gold-decorated bronze shaft, were both found in the excavation of Ugarit. Although iron objects dating from the Bronze Age have been found across the eastern Mediterranean, bronze work appears to have greatly predominated during this period. By the 12th century BC, iron smelting and forging of weapons and tools was common from sub-Saharan Africa through India. As the technology spread, iron came to replace bronze as the dominant metal used for tools and weapons across the eastern Mediterranean. Iron was originally smelted in bloomeries, furnaces where bellows were used to force air through pile of iron ore and burning charcoal. The carbon monoxide produced by the charcoal reduced the iron oxide from the ore to metallic iron. The bloomery, however, was not hot enough to melt the iron, so the metal collected in the bottom of the furnace as a spongy mass, or bloom. Workers then repeatedly beat and folded it to force out the molten slag. This laborious, time-consuming process produced wrought iron, a malleable but fairly soft alloy. Concurrent with the transition from bronze to iron was the discovery of carburization, the process of adding carbon to wrought iron. While the iron bloom contained some carbon, the subsequent hot working oxidized most of it. Smiths in the Middle East discovered that wrought iron could be turned into a much harder product by heating the finished piece in a bed of charcoal, and then quenching it in water or oil. This procedure turned the outer layers of the piece into steel, an alloy of iron and iron carbides, with an inner core of less brittle iron. Theories on the origin of iron smelting. The development of iron smelting was traditionally attributed to the Hittites of Anatolia of the Late Bronze Age. It was believed that they maintained a monopoly on iron working, and that their empire had been based on that advantage. According to that theory, the ancient Sea peoples, who invaded the eastern Mediterranean and destroyed the Hittite Empire at the end of the Late Bronze Age, were responsible for spreading the knowledge through the region. This theory is no longer held in the mainstream of scholarship, since there is no archaeological evidence of the alleged Hittite monopoly. While there are some iron objects from Bronze Age Anatolia, the number is comparable to iron objects found in Egypt and other places of the same time period. and only a small number of those objects were weapons. A more recent theory claims that the development of iron technology was driven by the disruption of the copper and tin trade routes, due to the collapse of the empires at the end of the Late Bronze Age. These metals, especially tin, were not widely available and metal workers had to transport them over long distances, whereas iron ores were widely available. However, no known archaeological evidence suggests a shortage of bronze or tin in the early Iron Age. Bronze objects remained abundant, and these objects have the same percentage of tin as those from the Late Bronze Age. Indian subcontinent. The history of metallurgy in the Indian subcontinent began in the second millennium BC. Archaeological sites in Gangetic plains have yielded iron implements dated between 1800 to 1200 BC. By the early 13th century BC, iron smelting was practiced on a large scale in India. In southern India, iron was in use 12th to 11th centuries BC. The technology of iron metallurgy advanced in the politically stable Maurya period, and during a period of peaceful settlements in the first millennium BC. Iron artifacts such as spikes, knives, daggers, arrowheads, bowls, spoons, saucepans, axes, chisels, tongs, door fittings, etc., dated from 600 to 200 BC, have been discovered at several archaeological sites of India. The Greek historian Herodotus read the first Western account of the use of iron in India. The Indian mythological texts, the Upanishads, have mentions of weaving, pottery, and metallurgy as well. The Romans had high regard for the excellence of steel from India in the time of the Gupta Empire, perhaps as early as 500 BC, although certainly by 200 AD, high-quality steel was produced in southern India by the crucible technique. In this system, high-purity wrought iron, charcoal, and glass were mixed in a crucible and heated until the iron melted and absorbed the carbon. Iron chain was used in Indian suspension bridges as early as the 4th century. Wood steel was produced in India and Sri Lanka from around 300 BC. Wood steel is famous from classical antiquity for its durability and ability to hold an edge. When asked by King Porus to select a gift, Alexander is said to have chosen, over gold or silver, 30 pounds of steel. Wood steel was originally a complex alloy with iron as its main component together with various trace elements. Recent studies have suggested that its qualities may have been due to the formation of carbon nanotubes in the metal. According to Will Durant, the technology passed to the Persians and from them to Arabs who spread it through the Middle East. In the 16th century, the Dutch carried the technology from South India to Europe, where it was mass-produced. Steel was produced in Sri Lanka from 300 BC by furnaces blown by the monsoon winds. The furnaces were dug into the crests of hills, and the wind was diverted into the air vents by long trenches. This arrangement created a zone of high pressure at the entrance, and a zone of low pressure at the top of the furnace. The flow is believed to have allowed high temperatures than bellows-driven furnaces could produce, resulting in better quality iron. Steel made in Sri Lanka was traded extensively within the region and in the Islamic world. See also steel #Wood Steel and Damascus Steel. One of the world's foremost metallurgical curiosities is an iron pillar located in the QUTB complex, Delhi. The pillar is made of wrought iron, is almost 7 meters high and weighs more than 6 tons. The pillar was erected by Chandragupta II Vikramaditya and has withstood 1,600 years of exposure to heavy rains with relatively little corrosion. Iron Age European working was introduced to Greece in the late 10th century BC. The earliest marks of Iron Age in Central Europe are artifacts from the Hallstatt Sea culture. Throughout the 7th to 6th centuries BC, iron artifacts remained luxury items reserved for an elite. This changed dramatically shortly after 500 BC with the rise of the Latine culture, from which time iron metallurgy also became common in Northern Europe and Britain. The spread of ironworking in Central and Western Europe is associated with Celtic expansion. By the 1st century BC, Meteoric steel was famous for its quality and sought after by the Roman military. The annual iron output of the Roman Empire is estimated at 84,750 t, while the similarly populous Han China produced around 5,000 t. China historians debate whether bloomery-based ironworking ever spread to China from the Middle East. One theory suggests that metallurgy was introduced through Central Asia. The earliest cast iron artifacts, dating to 5th century BC, were discovered by archaeologists in what is now modern Luo County, Jiangsu in China. Cast iron was used in ancient China for warfare, agriculture, and architecture. Around 500 BC, metal workers in the southern state of Wu achieved a temperature of 1130 degrees Celsius. At this temperature, iron combines with 4.3% carbon and melts. The liquid iron can be cast into molds, a method far less laborious than individually forging each piece of iron from a bloom. This technology would be known in Europe from early medieval times on. Cast iron is rather brittle and unsuitable for striking implements. It can, however, be decarburized to steel or wrought iron by heating it in air for several days. In China, these iron working methods spread northward, and by 300 BC, iron was the material of choice throughout China for most tools and weapons. A mass grave in Hebei province, dated to the early 3rd century BC, contains several soldiers buried with the weapons and other equipment. The artifacts recovered from this grave are variously made of wrought iron, cast iron, malleabilized cast iron, and quench-hardened steel, with only a few, probably ornamental, bronze weapons. During the Han Dynasty, the government established ironworking as a state monopoly and built a series of large blast furnaces in Henan province, each capable of producing several tons of iron per day. By this time, Chinese metallurgists had discovered how to find molten pig iron, stirring it in the open air until it lost its carbon and could be hammered. By the 1st century BC, Chinese metallurgists had found that wrought iron and cast iron could be melted together to yield an alloy of intermediate carbon content, that is, steel. According to legend, the sword of Liu Bang, the first Han emperor, was made in this fashion. Some texts of the era mention harmonizing the hard and the soft. In the context of ironworking, the phrase may refer to this process. The ancient city of Wan from the Han period forward was a major center of the iron and steel industry. Along with their original methods of forging steel, the Chinese had also adopted the production methods of creating wood steel, an idea imported from India to China by the 5th century AD. During Han Dynasty, the Chinese were also the first to apply hydraulic power in working the bellows of the blast furnace. This was recorded in the year 31 AD as an innovation of the engineer Du Shi, prefect of Nanyang. Although Du Shi was the first to apply water power to bellows in metallurgy, the first drawn and printed illustration of its operation with water power appeared in 1313 AD in the Yuan dynasty era text called the Nongxiu. In the 11th century, there is evidence of the production of steel in Song, China using two techniques. A Bergenesque method that produced inferior, heterogeneous steel, and a precursor to the modern Bessemer process that utilized partial decarbonization via repeated forging working under a cold blast. By the 11th century, there was a large amount of deforestation in China due to the iron industry's demands for charcoal. By this time, however, the Chinese had learned to use bituminous coke to replace charcoal, and with this switch in resources, many acres of prime timberland in China were spared. The change of fuel resources from charcoal to coal was pioneered in Roman Britain by the 2nd century AD, although it was also practiced in the Germanic Rhineland at the time. Africa south of the Sahara, inhabitants at Termit in eastern Niger became the first iron smelting people in West Africa around 1500 BC. Iron and copper working spread southward through the continent, reaching the Cape around AD 200. The widespread use of iron revolutionized the Bantu-speaking farming communities who adopted it, driving out and absorbing the rock tool-using hunter-gatherer societies they encountered as they expanded to farm wider areas of savanna. The technologically superior Bantu speakers spread across southern Africa and became wealthy and powerful, producing iron for tools and weapons in large industrial quantities. In the region of the Air Mountains in Niger, there are signs of independent copper smelting between 2500 and 1500 BC. The process was not in a developed state, indicating smelting was not foreign. It became mature about the 1500 BC. Similarly, smelting in bloomery-type furnaces in West Africa and forging for tools appear in the Nok culture in Africa by 500 BC. The earliest records of bloomery-type furnaces in East Africa are discoveries of smelted iron and carbon in Nubia and Axum that date back between 1500 BCE, particularly in Meroe. There are known to have been ancient bloomeries that produced metal tools for the Nubians and Kushites and produced surplus for their economy. In the regions of Tanzania inhabited by the Haya people, carbon dating has shown that blast furnaces were as old as 2,000 years, whereas steel of this caliber did not appear in Europe until several centuries later. Medieval Islamic world. Iron technology was further advanced by several inventions in medieval Islam during the so-called Islamic Golden Age. These included a variety of water-powered and wind-powered industrial mills for metal production, including geared grist mills and forges. By the 11th century, every province throughout the Muslim world had these industrial mills in operation. From Islamic Spain and North Africa in the west to the Middle East and Central Asia in the east, there are also 10th century references to cast iron, as well as archaeological evidence of blast furnaces being used in the Ayyubid and Mamluk empires from the 11th century, thus suggesting a diffusion of Chinese metal technology to the Islamic world. Geared grist mills were invented by Muslim engineers, and were used for crushing metallic cores before extraction. Grist mills in the Islamic world were often made from both water mills and windmills. In order to adapt water wheels for grist milling purposes, cams were used for raising and releasing trip hammers. The first forge driven by a hydropowered water mill rather than manual labor was invented in the 12th century Islamic Spain. One of the most famous steels produced in the medieval Near East was Damascus steel, used for sword making, and mostly produced in Damascus, Syria, in the period from 900 to 1750. This was produced using the Crucible Steel method, based on the earlier Indian wood steel. This process was adopted in the Middle East using locally produced steels. The exact process remains unknown, but it allowed carbides to precipitate out as microparticles arranged in sheets or bands within the body of a blade. carbides are far harder than the surrounding low-carbon steel, so swordsmiths could produce an edge that cut hard materials with the precipitated carbides, while the bands of softer steel let the sword as a whole remain tough and flexible. A team of researchers based at the Technical University of Dresden that uses X-rays and electron microscopy to examine Damascus steel discovered the presence of cementite nanowires and carbon nanotubes. Peter Paufler, a member of the Dresden team, says that these nanostructures give Damascus steel its distinctive properties and are a result of the forging process. Medieval and early modern Europe. There was no fundamental change in the technology of iron production in Europe for many centuries. European metalworkers continued to produce iron in bloomeries. However, the medieval period brought two developments: the use of water power in the bloomery process in various places, and the first European production in cast iron powered bloomeries. Sometime in the medieval period, water power was applied to the bloomery process. It is possible that this was at the Cistercian Abbey of Clairvaux as early as 1135, but it was certainly in use in early 13th century France and Sweden. In England, the first clear documentary evidence for this is the accounts of a forge of the Bishop of Durham, near Bedburn in 1408, but that was certainly not the first such ironworks. In the furnace district of England, powered bloomeries were in use into the beginning of the 18th century, and near Garstang until about 1770. The Catalan forge was a variety of powered bloomery. Bloomeries with hot blast were used in upstate New York in the mid-19th century. Blast furnace cast iron development lagged in Europe, as the smelters could only achieve temperatures of about 1000 C, or perhaps they did not want hotter temperature, as they were seeking to produce blooms as a precursor of wrought iron, not cast iron. Through a good portion of the Middle Ages, in Western Europe, iron was still being made by the working of iron blooms into wrought iron. Some of the earliest casting of iron in Europe occurred in Sweden, in two sites, Lafitin and Vineritin, between 1150 and 1350. Some scholars have speculated the practice followed the Mongols across Russia to these sites, but there is no clear proof of this hypothesis, and it would certainly not explain the pre-Mongol datings of many of these iron production centers. In any event, by the late 14th century, a market for cast iron goods began to form, as a demand developed for cast iron cannonballs. Osmond process. Iron from furnaces such as Lafitin was refined into wrought iron by the Osmond process. The pig iron from the furnace was melted in front of a blast of air and the droplets caught on a star. This formed a ball of iron, known as an Osmond. This was probably a traded commodity by c. 1200. Finery process. An alternative method of decarburizing pig iron was the finery process, which seems to have been devised in the region around Namur in the 15th century. By the end of that century, this Walloon process spread to the Pays de Bray on the eastern boundary of Normandy, and then to England, where it became the main method of making wrought iron by 1600. It was introduced to Sweden by Louis de Geer in the early 17th century and was used to make the Oregrounds iron favored by English steel makers. A variation on this was the German process. This became the main method of producing bar iron in Sweden. Mentation steel. In the early 17th century, ironworkers in Western Europe had developed the cementation process for carburizing wrought iron. Wrought iron bars and charcoal were packed into stone boxes, then held at a red heat for up to a week. During this time, carbon diffused into the iron, producing a product called cement steel or blister steel. One of the earliest places where this was used in England was at Coalbrookdale, where Sir Basil Brooke had two cementation furnaces. For a time in the 1610s, he owned a patent on the process, but had to surrender this in 1619. He probably used forest-of-the iron as his raw material, but it was soon found that ore-ground iron was more suitable. The quality of the steel could be improved by fagoting, producing the so-called shear steel. Crucible steel. In the 1740s, Benjamin Huntsman found a means of melting blister steel, made by the cementation process, in crucibles. The resulting crucible steel, usually cast in ingots, was more homogeneous than blister steel.